One application is that we can use this. So this theorem is called the graph container theorem or graph container lemma. We can use this graph container to count the number of intersecting families. So we know that there are, so what's intersecting family? So that's a collection of sets or family of sets where all the sets in there intersect each other. So arbitrary two of them intersect. So there are also lots of theory regarding this object. One of the famous one is the Ellis-Corrado theorem. For any n at least 2, every intersecting family in the vertex set n, there are n vertices, and then all the sets we consider are type K. So this is K uniform hypergraph. In K uniform hypergraph, you stay within intersecting, meaning that every two X have a common element that has size and most n should K. So this theorem is known, and this is tight by the example of star. So what's star? Star is you consider all the sets that contain specific element. You fix one element and then you consider all sets that contains the element. And let's say you only care about the uniform case. That's called the star. And it's called star because this analog is for the graph case. This is the case. You have one specific vertex and then every edge contains it, and it looks like star. Okay, so we know that. And one natural question is that counting for how many intersecting families are there in this n vertex K uniform hypergraph. How many intersecting hypergraphs are there? That's natural question. And trivial lower bound is that the number of intersecting families. One lower bound is 2 to the n minus 1 choose. What did I write? Oh, yeah, I wrote it wrong. Sorry. So this is the number. I mean, due to this star construction, this is natural. Then any subset of it is also intersecting family. Once you have a star, there are this many ones, and some of them you delete, some of them you keep, and you again get an intersecting family. So that provides all distinct intersecting families. So that gives us this lower bound. Then natural question is then what's upper bound? Can we find an upper bound that shows that this lower bound is quite tight? And the following theorem gives us an upper bound. This is proved by a log graph called view 잘했어야. And what they show for KLE3 and NLE2K plus 1, the number of intersecting families when the vertex set bracket n is 2 to the 1 plus little of 1 times n minus 1 to the k minus. So at least the exponent is asymptotically tight. And one noticeable thing is that here it's n is at least 2k, and here n is at least 2k plus 1. So this gap in the bound is necessary. Why? If n equals 2k, then we can actually get more. Then what? Then we pair up the sets with its complement. So A and complement of A, or this here is what? Half times n choose k pairs. Right? And what? In order to find an intersecting family, as long as these two are not there, not both there. So if it is here, and it intersects with every other thing because n is 2k, then as long as the other set of size k is not the complement, they intersect. So we have three choices. Either include nothing from this pair, or A, only A, or the complement of A. So there are three choices for each of them. So that is 3 to the half n choose k ways. And that's what? That's 3 to the n choose minus 1 choose k minus 1 ways to build an intersecting hyperbola, intersecting family. So that many distinct intersecting family, that's bigger than this. So when n equals 2k, this is not tight. This is not true. So this condition is necessary there. Okay. So how do we prove this? So again, our plan is to use the above graph container lemma. So in order to do that, we need to consider some graph, some auxiliary graph whose independent sets correspond to the object that we want to count. In this case, that's the intersecting family. So what are the graphs whose independent sets correspond to intersecting family? That is this Knazer graph. So the Knazer graph, let's write Kn and K is a graph with the vertex set being the all possible subsets of size K of the bracket N, and two sets, so two vertices that are adjacent. If and if they are disjoint. So when they are disjoint, you add an edge between them. Otherwise, you don't. But I think I heard that this is pronounced as Nether instead of Knazer. But lots of people say this is Knazer graph, so maybe I'll just say Knazer graph. But maybe the correct pronunciation is Nectar. Anyway, so now this is the correct graph. So here, if you consider an independent set here, that means there is an independent set, means that these vertices there are no edges between. That means they correspond to the sets whose intersection has an element. So that's intersecting family. So now what? we can simply count the number of independent sets in this Canadian graph. Then that provides a bound on the number of intersecting family on the fixed vertex set given. Okay, for that we want to use this correct container line. Then what do we have to show? We have to show that this graph is locally dense. And how do we show that? We can use some known feature. So we know that there is this theorem or lemma called the extender mixing lemma. We learned it in the introduction to the graph theory course. Say that if you have a deregular, say Brachiden, let's use Brachiden to denote the number of vertices here. Brachiden vertex. Maybe let's also use capital D here. Graph with say eigenvalues. Lambda 1, which is same as T, lambda 2, lambda n, and yeah, this is non-positive, negative number, and corresponding orthonormal eigenvector, say V1 to Vn, and that satisfies the following for all x and t, except that of g. What do we know? The number of edges between f and t. So in this expression, if f and t are not disjoint, unless there lies in both of them, I count it twice. So it counts f comma t, which are adjacent. In that case, this is f comma t and t comma f, both are counted. Anyway, that's same as you take adjacent matrix of A and you multiply these two vectors, the characteristic vector of A, F. So this is the vector, column vector, where 0, 1 vector. It's 1 if the coordinate belongs to the T, otherwise it's 0. And from there you can compute that. So this formula gives you the number of edges between F and T. Anyway, so from here we can actually get the lower bound. How? This is the smallest one, so you just replace every one of these at lambda n, and you do some computation. Then what? We can show that the number of edges in F is at least half times ESF, and you can show that if holds. So you can get the lower bound on the number of edges within such a set, or arbitrary, yes. Okay. So this is the smallest eigenvalue. This is not lambda times n. This is lambda sub n. And as long as we know the smallest eigenvalue, then we can get the lower bound of the number of edges in a specific set. So if this one is not too small, then you obtain locally dense condition. And known fact is that the minimum eigenvalue of this Schneider graph is negative n minus k minus 1 choose k minus 1. Combining these two, we can prove the following proposition. So for given epsilon, every subset f of the vertex set of this Schneider graph, so which is collection of sets. Each vertex is a set. So if it has more than this number of sets, that contains at least half times beta times the size of S square epsilon, where this beta is like epsilon over 2 times 1 plus epsilon k times n minus k minus 1 choose k minus 1 divided by k minus 1 times n minus 1 k minus 1. The specific expression is not so important, but the important thing is that we can show that the Schneider graph is locally dense with the correct parameter. And what we can use the graph container lemma for the above data, and R, capital R is 1 plus epsilon times minus 1 choose k minus 1, and small r is, you do the computation, then this is the number that's you want to take, log of n over 1 plus epsilon times k. Then number of independent sets in Canadian graph is at most what the capital N should R I'm what capital R choose k minus R, and then k you have to take from like R2 R plus R, but if you add this term all together, then you can simply get the upper bound of this. And this is what? This n should k should R, should be R plus R. So this term is here, and that's like 2 to the n minus 1 should k minus 1. And then this R, 2 to the R is what? 2 to the smaller R is roughly like some polynomial in n. And this is what? This is n should K over R to the R. Again, that's like N to the KR. That's like 2 to the polylogon N. Log N times K times R, which is also like log N. So bottom line is that this term is big. So 2 to the term N to the K. So this is roughly N to the K. And then all the other terms are like 2 to the log. And this is also 2 to the log N. So all the other things are small except this one term. So you can check that this is actually 2 to the like 1 plus 2 epsilon or 3 epsilon times and choose. Let's write it this way. So as we expected, so we can get it. Okay, so we learned about this graph container. And then here, the object that we were considering is intersecting family. And intersecting family, the key characteristic that we care about is pairwise relation. You have two sets, whether they intersect or not. That is what we want. So some objects is characterized by some binary conflict. And then we want to count the objects which does not contain this binary conflict. Then this graph container lemma is useful. And natural question is that what if the conflict that we care about is not binary? So in other words, graph is two uniform hypergraph. So two uniform conflict. So in the independent sets are the corresponding to the object that does not contain this binary conflict. But if we have a non-binary conflict, then it would be good if we have a corresponding container lemma for hypergraph. In the same split, Rowe, Morris, Hamotzi, and independently by Sexton and Thomason proved the following hypergraph container. As the statement is too technical, so I will not write in full detail. But the roughly idea is say if K uniform hypergraph H satisfies some locally dense condition, and there exists a family of container, say C, curly C, so which is collection of sets satisfying the value. One for every independent set I, there exists some set in this container which contain this I, and two, this container is small. So it doesn't mean there are not too many sets there. Also, the small is, I mean, you can quantify, but it's technical statement. And for each, if C, if it's almost independent. meaning that this contains only a few number of edges, number of hyper edges. So we can prove this. We can, actually prove more technical way that as here you have this sets, the S and A, and this SI is called fingerprint, and then you can also get similar statement here. But I will not introduce the more technical statement, but let me just give you this idea in this version. And this is useful in counting many mathematical objects. So for example, so this can actually show that, for example, the number of triangle polygraph on the vertex set bracket n is what? 2 to the 1 plus little of 1 times n squared over 4. We can use the hypergraph container to prove this. So here, whenever we say that this is on the vertex set bracket n, and on this bracket n set, vertex 1 and vertex 2 are different. So this is counting the vertex labeled graph. Same with the previous intersecting graph, intersecting family example. So for example, if you have this 1, 2, 3, this graph, and then 1, 2, 3, this graph are different graphs, even though they are isomorphic. So we don't count the number of isomorphism graph, we count the graph on the vertex graph. Okay, there, so this is the upper bound. Lower bound is easy, so you take a complete bipartite graph and any subgraph. Any subgraph is triangle free. So 2 to the n squared over 4 is the lower bound. Then this gives us the almost similar upper bound. In fact, this was previously proved by Erdish, Kleitman, Rothschild. And then they actually proved a stronger statement that almost all triangle free graphs on vertex set bracket n is bipartite. So here, the little one is on the exponent. But what they show is that the lower bound is the number of bipartite graphs. And that's like, say, X. And then upper bound, so this is the number of triangle free graphs. The upper bound is 1 plus epsilon times the number of bipartite graphs. So that's what Erdic, Kreiman, and Rothschild show. In that case, what? You count all the different triangle free graphs. And then among them, you count all the bipartite graphs. And remaining is negligible portion. So this 1 plus epsilon is multiplied in front of it. On the other hand, this counting, this is on the top. So we don't know. This does not imply this, but this implies this. So this direction is fine. This does not imply. So this is actually stronger statement. Also, another example is that we say a subset A of bracket N is called the sum free if there are no x, y, z with x plus y equals z. Then what? We know that if sum free is give you size at most half. How? You can take all odd numbers and that gives you a sum free set, or all numbers greater than n over 2. And that gives you also size half set. As any subset of this give you a sum free set, so lower bound is 2 to the half n. It's lower bound. And actually, I mean, yeah, so that's a lower bound. And again, using this hypergraph container, you can show that the number of sum free subsets of bracket n is at most 2 to the r plus little of 1, and then you can show this. And see that here, the conflict is not binary, trinary. You have 3 things, x, y, z together, it cannot be in here. 2 of them is fine, but what we want to avoid is these 3. Here, again, what? Triangle free. So if h, if h, if h. So here, we count the graph. So what do we consider? So you have a graph. And then for each pair, here, it's either added or not, added or not. So you can consider the hypergraph with vertex set if the pairs of the vertices here. So this vertex is bracket n, and all the pairs are here. And then edges are what? A, B, B, C, C, A. So that's the triangle that we want to avoid. There you consider the independent set, then that corresponds to a triangular polygraph here. And again here, you have what? X, Y, Z. Consider X, Y, Z as a hyperedge if X plus Y equals Z. And there you consider an independent set that corresponds to the sum free subsets. Okay, so these are among many applications. I mean, these are 2, and maybe we can consider one more application of this hypergraph container lemma. And we'll talk about that in the next video.